Thanks, Aisha. So like Aisha said, I spent my summer looking at how avulsion frequency is affected by rising sea levels. So avulsions are just abrupt channel jumping events, so the flow path changes abruptly. So here on the bottom, we have two images of the Yellow River Delta. And so on the left is an image from 2001, and on the right is an image from 2009. And on the 2009 image, we can see that there was some type of avulsion that occurred. We can see a shift in the channel path. So why do we care about avulsions? Well, most coastal river deltas are relatively flat, and so they're susceptible to drowning by subsidence and sea level rise. Well, avulsions help deliver sediment to those areas that are drowning. So again, in the 2009 image, we see that there was some type of land growth where that avulsion occurred. Even though avulsions help counteract sea level rise and subsidence, they also pose natural hazards. So on the left, we have an image of the 2008 Kosi River avulsion. Because river avulsions are very abrupt, they can cause large infrastructural and economic impacts as well. So the Kosi River actually shifted 120 kilometers eastward and ended up affecting approximately 3 million people. So you can see that there can be a lot of effects from river avulsions. So there has been previous work studying the location and frequency of avulsions on coastal river deltas, but most of those studies have focused on having a constant sea level. So my project for the summer looked at incorporating a sea level rise to see how those river avulsions would be affected, or at least in terms of the frequency. So do they happen less often, more often, or does the frequency that over which they occur not change at all? So we can define the avulsion frequency or the avulsion time as the amount of in-channel sedimentation that occurs in the river channel over the rate over which that in-channel sedimentation occurs. So here I have a cartoon of a river channel. So this is cross-sectional view. So that blue line that you see is the water surface. So the amount of in-channel sedimentation that occurs to where an avulsion is initiated is our H-fill variable, or the amount of in-channel sedimentation. And then the rate over which that vertical aggradation or in-channel sedimentation occurs is our BA. So river avulsions are very difficult to observe in nature because they're very rare occurrences. So we can use physical experiments to make observations that we otherwise wouldn't be able to see in a natural environment. So on the left, we have a schematic of the delta flume, which we used to help model the river avulsions. So we have the delta flume consists of a 7-meter long by 14-centimeter wide alluvial river, which empties into a 6-meter long by 3-meter wide ocean basin. And we fed sediment and water at the uppermost portion of the alluvial river. We also had cameras attached on an external frame surrounding the delta to capture overhead images and video. And we also had a motorized instrumentation cart, which had some triangulation, some laser triangulation sensors, which allowed us to scan the delta and extract topographic data. On the top right, we have kind of a schematic of the flow experiment. So the experiment thus far has consisted of phase 1, over which we kept constant sea level, and phase 2, where we increased sea level to 0.25 millimeters per hour. And through these phases, we alternated between high and low discharges, so variable discharges through time. And here on the bottom, you can see a picture of me inputting tracer dye. It was a lot of fun. So Because these experiments have to be scaled similarly to natural environments such as the Yellow River Delta or the Mississippi Delta, they take a very long time to conduct in a laboratory setting. So the experiment had actually already been running for approximately 6 months prior to when I joined the summer, and it's still projected to run for another 2 or 3 months. So we use those overhead images to as a reference to identify our avulsions. So on the left, or top left, we have an image where I identified the new channel and the old channel, and the blue arrow is the flow direction. So the time between each avulsion is our avulsion time, or our T sub A. We use that topographic data that was extracted to first extract channel levees for the initial scan over which the avulsion took place, and then the final scan as well. So by extracting those levees, I was able to calculate the cross-sectional area of the channel, and we were able to then difference those amounts to determine the amount of in-channel sedimentation that occurred. So I just want to show you guys a 30-second time-lapse video of the experiment to date. So the flow is coming out from the river on the left. The red that you're seeing is land that's being built up. The green is the ocean. So you can see that the channel is laterally migrating. That's those sweeping motions. And in between those lateral migrations, we have the abrupt avulsions. During phase 2, during our increase in sea level rise, we also see an increase in the frequency over which avulsions occur, and we see that there's also a lot more wedge building to try and deliver sediment to those drowned areas. So here, I'm just kind of digging down into 2 avulsions that took place. On the top, I have an image of an avulsion from phase 1, and on the bottom, I have an image from phase 2. So when we compared the avulsions from phase 1 and phase 2, we found that the avulsions occurred more frequently in phase 2. So here on the figure, or on the box plot figure on the right, we have our phases on the x-axis, so constant sea level and the sea level rise case, and on the y-axis we have the time between avulsions. So we can see that during our phase 2 they do happen a little bit more frequently. So even though they happen, so we found that they do happen more frequently, right? That the avulsion cycle is somehow influenced by sea level rise, but is it the amount of in-channel sedimentation that is influenced by that sea level rise, or is it the rate over which that in-channel sedimentation occurs that's being affected? So here I have a graph with distance on the x-axis and normalized in-channel sedimentation on the y-axis. And the normalized in-channel sedimentation is just the difference between the initial and final times of the avulsion cycle divided by the characteristic channel depth. And this just gives us an idea of which proportion of the characteristic channel depth does that in-channel sedimentation reach a threshold over which the avulsions are initiated. So when we look at the graph, we find that our in-channel sedimentation tended to reach an avulsion threshold at approximately a little bit more than 60% of the characteristic channel depth for both phase 1 and phase 2. And phase 1 is that dashed line, and phase 2 is a solid gray line. So was the rate influenced by sea level rise? So I have the same images on the left. On our figure on the right, I have time on the x-axis, and again, normalized in-channel sedimentation, but this time at the avulsion node on the y. So again, phase 1 is that dashed line, phase 2 is a solid line, and that red dashed line is the avulsion threshold, which is the same as the previous figure. So we see that for phase 2, that solid line, that the avulsion, or the time it takes to reach that avulsion threshold, is reached a lot more quickly than during phase 1. So just to kind of rehash some of the findings that we saw. So does sea level rise affect the avulsion frequency? And we found that, yes, in fact, it does. Avulsions tend to happen more frequently when there is sea level rise. Was the critical amount of in-channel sedimentation needed to initiate an avulsion affected by the sea level rise? And we found that regardless of that sea level rise, during both cases, we reached the same threshold over which an avulsion were to take place. And is the rate of in-channel sedimentation needed to initiate an avulsion influenced by sea level rise? And we found that avulsions are more frequent because they reach that threshold a lot more quickly. So future work can look at implementing more variables. So here we isolated avulsion frequency and where they occurred based on sea level rise, but deltas are very dynamic landscapes, so there's vegetation, there's tides, waves, so that could lead into future work for these types of experiments. We also used a non-cohesive sediment to try and mimic natural settings, so that could also be an area that we might look into. Implications for the type of work that I got to do over the summer. So this can tie into current models and help strengthen them so that we can better predict when these avulsions might occur. And so I just want to thank UNAVCO, RESESS for their support, our awesome graduate assistant, NSF for funding, ExxonMobil, and then also my mentors at Caltech who let me work in their lab this summer. So, any questions?
I noticed that your model basically took in sort of a regular distribution of changes in discharge. Is there any sort of plan to sort of look at sort of climate models and changes in precipitation, anticipated changes in precipitation, and apply that to this model?
That could be something for the future. So the changes in flow discharge were included to mimic backwater hydrodynamics in delta systems, which is what we see in natural settings. I didn't go into that because it can get a little bit more complicated, but essentially we were trying to mimic the length of the channel over which non-uniform flow occurs. But that could be some type of future work.
I had some basic questions about avulsions and the experiment. In nature, how long does it take an avulsion to happen? Like when you said that happened in 2008, I guess how quick was it? And then for your experiment, like the 9 months, is that per phase or is, oh, okay, so that is really slow. Oh, no, okay, yeah, I was just wondering if that was per phase or like, yeah, just how the time scale exactly.
Okay, so to answer your first question, if we use the Yellow River Delta as an example, avulsions occur like approximately every 10 years. In the Mississippi River Delta, it's been found that avulsions occur every 1,000 years. So think of it kind of like an earthquake. There's still a lot more modeling to be done to understand the frequency that these are going to occur. So we want to be able to predict when they'll occur so that we're ready, so that there isn't as much damage.
So using the earthquake analogy again, like an earthquake happens really quickly, like 5 minutes. So when an avulsion actually happens, I guess, like how long does it take to just switch directions?
I probably can't answer that for you, only because when an avulsion occurs, so essentially the bed degrades to a certain point, the channel becomes unstable, and so you have overland flow or sheet flow, so it breaks the levee, you have a break in the levee, and then it finds a new path, and then that path becomes the main channel. But I'm not sure as far as like how long that process takes. I wouldn't be able to tell you that. And then could you repeat your second question that you had?
How long does each phase of the experiment
So
take?
when I got to Caltech this summer, I believe they had just finished up phase 1. So this experiment so far has approximately 70 or 80 hours runtime, but I think there was maybe like 10 hours of phase 2 that had already been started, and so we were trying to finish up phase 2 at when I left. But you also have to take into account like equipment breaking, and the prep time for these experiments is pretty long. Yeah.
Other questions?
Shelley.
Once you have a chance to run through these experiments multiple times, if you were going to be talking with coastal policy managers about the risk of a natural disaster, of an avulsion happening, what would you try to communicate based on your results?
So at this point, I think it would be very difficult for me to make any type of communication other than preliminary results would show that with some type of sea level rise, that avulsions tend to occur more frequently. So that would be all I could say at this point.
Okay. Wait. Are you ready to talk or you have a question? Oh, okay.
So what kinds of mitigation efforts are being made to reduce the effects of river avulsions and channel avulsions?
So at this point, I'm not quite sure what type of mitigations are in place other than, like, when you look at the Mississippi area, they do have, like, super high, engineered levees. But what we're looking at is relatively new work. So it's still fairly recent. So that communication might come later once we have a lot more data and we're able to, for sure say, what's going on.